Good morning, dear students. In the class of BSc Part First, Subject Physics and Paper Second, we are dealing with electromagnetic induction. In the earlier lectures, I told you about the phenomena, the experiments performed by Michael Faraday. Then I defined Lenz's law, and I told you some questions based upon that particular topic. After this, I discussed about the coefficient of self-induction, and we determine coefficient of self-induction for a coil and for a solenoid. Then, dear students, in the last lecture, I discussed the Faraday's law of electromagnetic induction in its differential and integral form. And you were able to understand that how a variable magnetic field or flux with respect to time associated with any closed circuit is able to induce electric field and hence potential and current. The important point which I pointed out was that the induced electric field is always a non-conservative field. Today I shall tell you about the aspect of second Faraday's experiment. If you recall, in the second experiment there was one coil. Say I will call this as coil number 1, and there was an arrangement to change the current associated with it. There was a nearby circuit with which a galvanometer was attached. And if you recall, whenever this current in the circuit first, this is circuit second, whenever the electric current in the circuit first is changed, a deflection is observed in the galvanometer which is associated or connected to the second circuit. How can you explain is that whenever the current is passed through the first circuit, the magnetic field lines passes through the nearby circuit. So I am changing current in this circuit and the flux associated with the second circuit is changing. And change of this flux is causing an induced EMF or current in the second circuit. Dear students, this phenomena in which changing current in one circuit causes an induced EMF in the nearby circuit is defined as electromagnetic induction, mutual electromagnetic induction. So today I shall discuss this mutual induction. I would like to tell you very clearly that whenever we are studying mutual induction, it does not mean that self-induction is gone. No. Self-induction is an intrinsic property of every circuit. So that will be there with these circuits. But changing the current in one circuit always causes an induced EMF in the nearby circuit. And this phenomena is called mutual induction. So whenever the magnetic field lines produced in one circuit are passing through the circuit nearby, it is called magnetic coupling. So I am writing the definition like this. Whenever by changing the current in one circuit the magnetic flux associated with a nearby circuit changes, and hence induced EMF takes place. The phenomena is defined as mutual induction. It's called mutual induction. The circuit in which current is changed is normally called primary circuit, and the other nearby circuit is called secondary circuit. If phi 2 is flux associated in secondary circuit and I1 is current in primary circuit, then dear students, phi 2 is directly proportional to I1, and I get a constant MI1. M is called coefficient of mutual induction. I would like to tell you that unit and dimensions of M are the same as that of self-induction coefficient. That means it is Henry. Since current I1 is changing with time, that's why phi 2 changes. So associated induced EMF E2 will be minus d phi 2 upon dt, and that will be minus m d I1 upon dt, minus m d I1 upon dt, rate of change of current with respect to time. And you can say mode of E2 divided by di1 upon dt. If di1 upon dt is 1 ampere per second, I would like to tell you that numerically it is equal to, many books define coefficient of self-induction by this way, that whenever when the rate of change of current associated with the primary circuit is unit, the induced EMF in the secondary circuit is equal to the coefficient of their mutual induction. Now I shall tell you about the calculation of coefficient of mutual induction of different circuits.